Welcome. My name is Eli Schwartz. I've been teaching chemistry for about 15 years now, and I'm excited to jump in today and help you out with some of yours. Specifically, these three main learning goals, dealing with deriving units, talking about conversion factors, and of course, dimensional analysis with some real problems. First up, let's start with understanding a little bit about terms, essentially, to describe how much stuff we have. In terms of how much stuff we have, there are a couple uncommon ones that are a little bit more advanced, like spin or charge at the molecular level, but these ones here are the most common ones we're likely to start with first, things like length or mass or temperature. And really, you may already know some of these terms because in your everyday life, you're probably describing at least a few of these. Let's start maybe with something like a warm-up. Let's take length. You might have described physical stuff in the past, like a type of length or distance. Off the top of my head, let's see, a mile or foot or an inch, maybe a centimeter, cubit, furlong. Let me type a couple of these out here. Maybe a fathom or a yard, or if we're going really small, an angstrom. Here we go. Here are just a few, again, that I'm thinking of off the top of my head that would be units of length. Now, of course, some of these are a little bit archaic, like a fathom or a cubit. Some of them are super big, like a parsec or a light year. But notice we can talk about the same thing, length, with different units. Maybe a more real-world example. How about this? This is just one football field. A football field has a specific length, so it could be a unit in and of itself, right? It's one football field length by definition. Or we could break that down and measure it in yards. This section over here on the far left, well, this is 10 yards. And then for the entire field, that would mean it's 120 yards in total. Now we could, of course, go into smaller units. We could break it down into feet. This section over here on the left would then be 30 feet's worth. And doing the math, the entire field is 360 feet total. Clearly, there are some worse units that could be used to measure things. Like you wouldn't want to measure a football field with lengths of stuff in millimeters or smaller than that. It would just be annoying. So let's go a little bit further down this track then. How about amount of stuff? Any words that off the top of your head might mean amount? Of course, I've got one or two that I would think of. Probably, let me type a few of these. Maybe dozen or gross or score or mole, of course, classic for chemistry. But I just put a little note here. These are not values so much as they're just numbers, right? We don't have a unit attached to them. So a mole is not a certain amount of length. It's just an amount by itself. All pure values with no actual units. So if I wanted to count something, I could count up a dozen roses or dozen donuts or a dozen moons. It's very easy to pick apart because I'm counting a specific thing. I could use those. But maybe there are some terms, let's get a little bit fancier, where we would care about the actual thing. Like if I was dealing with weight, I might use pounds, or some value for volume, I might use gallons or cups or ounces. If it's sound, I might use decibels. If it's weight, I might use kilograms. If it's angles, I might use radians. I'm just typing as I'm going here. I've got just a general list of a bunch of specific units here on screen. So I could measure water in gallons or teaspoons or cups, and even though it's the same total amount of water, it's different values for those units. You might see how this could be a little confusing if we didn't start standardizing these values a little bit. And that's why, of course, we have System International units, or the International System of Standard Values. And it's possible even that you're already using the International SI units for length or mass or temperature or time already. The actual SI units, I'll go ahead and put these up here on screen as we go. Let's see, for length, we would be dealing with meters. For mass, we are dealing with kilograms. For seconds, for time, excuse me, we will be playing with seconds. for temperature. Now watch out, temperature, some people use degrees Celsius a lot in science, but technically degree Kelvin is our SI unit. And then a mole is our amount of stuff, our standard amount of stuff, which is 6.022 times 10 to the 23rd. I don't have a fancy way of doing superscript, so you'll have to use the caret. And that is our total amount of stuff. So again, for counting, like we used before, instead of using a dozen or a gross or something, I'll use a mole of things. I know this is a massive number compared to some of these others, like a second or a meter, which are relatively small. But these are the SI units, the values we've decided make sense for everybody to use to standardize. Now, we brought up a bunch of different units earlier when I just put random units up on screen, like hertz or fathom or radians. And I put miles per hour up there a minute ago because it's an example of combining two base quantities, in this case, miles and hours, right? Mile per hour. For chemistry, we have standards that are used most frequently in lab settings. And some of those require us to do a little bit of deriving physical quantities, combining a couple different values together. Let's take an example that might be a little bit of a nuisance to a lot of people, and that's molar concentration, the third one down on our list. Take a look. Suppose I have a length, 10 centimeters here off to the left, and I want to use that as a template to maybe do a section off a perfect cube here in this box I have on the right-hand side. Perfect, a 10 centimeter, 10 centimeter, 10 centimeter cube. Let's fill this in, because we've got volume now, with some water. Now suppose I want to toss an amount of stuff into that water, like maybe a convenient pile of atoms I have right here. And let's just say, for convenience, that it's exactly 1 mole's worth. Now, tossing that into the water, it should spread out and dissolve evenly. And that means I have 1 mole per this nice 10 centimeter, 10 centimeter, 10 centimeter cube, which happens to be a liter. 10 centimeter, 10 centimeter, 10 centimeter is exactly 1 liter worth, or 1,000 milliliters worth of water. So this gives me a mole per liter. Perfect. That's concentration. Done. Now there are SI derived units besides the units that we just saw here on screen. Actually, it might seem a little bit counterintuitive, but the SI derived units are not actually ones that we tend to use that frequently in a laboratory setting. For example, volume would be, well, I need to have length by length by length to have a volume, so that would be meters cubed. Again, we just saw a second ago liters. Usually I use liters, which is centimeters cubed, right? 10 centimeter, 10 centimeter, 10 centimeter, which is 1,000 centimeters cubed, or of course, 1,000 milliliters. But for SI, we would use meters cubed, which is actually 1,000 liters. For density, we would have to have a amount of mass per volume, so that would be kilograms per meters cubed. Nothing too crazy so far. Moles, of course, for molar concentration, would have to be moles per meter cubed, not per liter. Again, this would only really make our math a little bit different if we're doing a unit conversion problem to get them to SI units if we're being given something that has liters or milliliters in it. We'll get to that in a little bit later. For pressure, that would be kilograms, meters, times seconds squared, all in the denominator. Now, of course, that comes from a fancy way of deriving pressure, which is our force per unit area, and force is in kilograms, meters per second squared in the first place. I'm not going to show you the whole derivation of the unit, but it is the SI unit that is for pressure. And for molar mass, I have to have kilograms, which is my mass value, per mole, because that is our molar conversion value. Again, these are just derived SI units. And you might have recognized other terms I've used so far, like centimeters or milliliters or liters, and not so much the ones I just put up on slide. They look a bit stark, maybe, compared to the units you might be used to. And this is reasonable to expect because, as we've gotten our final bullet point, chemists don't always use, for convenience sake, the same terms that the International System of Chemists has decided is the standard unit value. This is somewhat okay, but it is something that we should be aware of. For example, all the way down the line here, we have a bunch of different values for volume or density or pressure that we would normally see in a laboratory setting. If we're looking for just the SI units ones, The only one here that actually is pure SI unit is the Pascal for molar concentration. That's it. That's the only one that actually matches up exactly to a value from SI. Everything else is not actually an SI unit. Done. I say done, but this is our first goal that we have to talk about in today's session. The second one is to do a little bit of conversion with the units that we're just learning a tiny bit about so far. And some of that conversion, of course, like we're able to do with the football field, is just going back and forth the exact same value, but just different units to represent it. For example, let's suppose that I wanted to convert in such a way to have the same quantity, but different units representing it. I have a gallon of milk, and I want to convert it into cups. That's unit conversion. Now, in order to do the math, I need to tell you exactly what we started with. So I'd say we have exactly 2 gallons of milk. The quantity is 2, the unit is gallons. We've got both things given. Now all we have to find out is, well, what we're converting into. So let's say I'm converting it into cups, like I said my example would be, and the desired unit then would be cups. The desired amount requires a little bit of math. There are 16 cups in a gallon, so we have 2 gallons, so 16 times 2 is 32 total cups. 32. That's the desired quantity. That's what we're shooting for here. So let's do a little bit of a sample problem that might look a little bit more scientific. We'd use this kilometers after all. And I want to convert kilometers and miles back and forth. So let's start with what we're given. Given 52. Right? 52 is the given thing. And since they're asking for given quantity in this, the given quantity is 52. The unit would be miles. The desired, well, the desired quantity, we don't know. We're going to have to solve for. We need to calculate. So let's see, we have 52 is the thing that has been given. And we know that 1 mile gives us 1.6 kilometers. So that's what we're going to use to convert. For every one of these 52 miles, we need to have 1.6 kilometers come back out. So I could multiply this essentially by 1.6 kilometers to get 83.2 kilometers out. Now the thing is, what we're really doing here is applying a conversion factor in one step. And for those of you following the units, you might say to yourself, but Eli, aren't I getting out 52 miles times 1.6? Isn't that going to be a mile kilometer? Well, because of this equals thing here, what we really did was we secretly, in that conversion, we're multiplying by 1.6 kilometers per mile. We didn't talk about it, but that's what we were really doing, because that is a true statement. We're multiplying essentially 52 by 1, so that we can exactly cancel out the miles in the denominator, and we're left with kilometers in the end. This is what we mean by applying a conversion factor. Now, again, a lot of us could do this in our heads maybe, because it's just a one-to-one, one step. There are other types of problems where we might be able to also do a lot of work in our head as well. For example, playing with standard SI conventions, playing with powers of 10, like millimeters to meters, or back and forth, like you see here in the 2 possible conversions. This is pretty fast, because we're just multiplying by a single value to get the prefix or the conversion factor into a different power of 10. But for any conversion, we can just take the given unit in any number of small steps, convert that to a new unit. Let's try that out on that same last problem before moving on to a new one, but see that spelled out a little bit more clearly in each of the steps. Often, we don't really actually focus on quantity like that problem was asking about right away. We look at units first. So the desired unit that we want is in kilometers, and we have given unit of miles, and we have 52 of them. But we need to cancel miles and leave ourselves with just kilometers only. Perfect. There's that conversion factor we saw a second ago. Now notice, the conversion factor we've written out here as a lovely fraction where miles is on the bottom because we want to cancel that out. We already have miles in the first place, and we want to get rid of it. And kilometers is on the top because that's what we want to end with. We want kilometers to be the value that is our final number. Now we're done. We just multiply 52 times 1.6, and just like we did earlier, we get 83.2. Done. And this is just really a more systematic way of setting up the problem we tried in quick shorthand earlier. That way we don't make any mistakes by accident. Let's do this again with a little bit more difficult looking problem. We want to know, all right, given 1 rupee units, desired unknown, but we want it to be in yen, so our given quantity, well, 1, desired quantity, some amount of yen, and there's some conversion factors in here. We can convert dollars to yen, we can convert dollars to rupees, we could really convert rupees to yen directly. It would be a little bit more work to set up to make sure we didn't make a mistake, but we absolutely could. If we want to do it in a couple steps though, not just one direct step with a kind of a messy fraction dealing with 112 and 68s all at once, we could do it a little bit slower with that same setup from a second ago. Let's set up our system with our desired unit and our given unit. In this case, our desired is in yen. Our given is rupee, and we have 1 rupee specifically. And we want to convert that rupee somehow. Maybe we'll do one step at a time. Let's convert the rupee to dollar, because we have this nice convenient $1 value. Now I'm canceling out my rupee in the bottom, but I'm left with dollars. I don't want to end in dollars. I have to remember I'm shooting for yen. So now I still have a conversion I can do, $1 to 112 yen, but remember I'm canceling dollar. I don't want dollar in the numerator again. I want dollar to be in the bottom. So times 112 yen per dollar means now I can cancel the dollars, and I'm left, canceled rupee, canceled dollar, left with yen, perfect. Now I just multiply across. Multiply 1 by 1 over 68 times 112. That gives me 1.65 yen, and all we've done here is calculated for quantity in the end after we went through and made sure very carefully that we had canceled out the units. And really that's our last main point here, is to remember, even with multiple parts, as long as we're multiplying by 1, canceling one thing out step by step, we're building towards a new unit. We want to do this in parts maybe at first, because that's a little bit easier. And again, it makes sure that we cancel so that before we do any of that math, we know that we're getting the right answer. Actually, we could do it in parts, not even like we just did, where we did part by part by part in one problem. You could do it by parts separately, right? Do the math, get an answer, and then do another part separately, like with this horse problem that you have in your sheet. First of all, I know we would never really do this on a test, but just for fun, let's get a picture of that horse. Not that we need to draw it for any reason, it's just fun. So our first step, of course, would be to set up our initial conversion. So I want to have, let's say, something in between feet and hands, and they've given us a conversion between hands and inches. So I'll convert to inches first from my original value of hands. And of course, they give us that conversion right here on screen. 1 hand is 4 inches. So multiply this by 4 inches, that's what I want to end with, divided by 1 hand, so hands cancel. Multiply the value, gives us 72. Good so far. Let's go a little bit deeper into this. I'm not done. They wanted the answer in feet, and I have inches. So, okay, so I want feet, and I have inches. Again, this is just a separate step unit conversion. I could have done this all at once, but I'm going to do it in pieces just to carefully check my work. All right, to convert inches to feet, it doesn't have it here on screen, but one of the values that we should have memorized is that there's 1 foot for 12 inches, just like there's 3 feet per yard. Standard values that we would be expected to memorize just from growing up and living in the real world. Now I cancel my inches, check. Feet is on the numerator, done. Now multiply across, do the math. 72 divided by 12, because 12 is in the denominator, means I'm left with 6 feet. Math done, finished. Now, at this point, let's try out actually one of the hardest problems of the day. I know we're only about halfway through the lesson, but this is one of the hardest ones we have because it's really a realistic chemistry problem that you might see in one of your classes. It's pretty complex for many students, but we're going to tackle it systematically in the same way we did before. what we need to know are one or two basic things. We'd have to be able to play around with understanding the desired amount, the given amount, and how to really get back and forth between that and H2O and oxygen. And some numbers are going to have to come into play for that. Just to be clear, our given quantity is 7.35. Our desired quantity, and really our desired units, is we want to find out how much gram H2O are we going to end up with. Okay, well, I have moles. I have a relationship here of 1 mole for every 2 water, but I don't have any value that converts over to anything in grams. Sounds like I'm going to need something that gives me moles to grams conversion. Conveniently for us, the periodic table does exactly that. In this case, I'm playing around with just making sure I get the right values before I go any further. I need water, and water, in case you can't read on that tiny type, is 1 as its number underneath the name hydrogen. It says 1. Now 1 represents 1 gram per mole. Wonderful. That's a nice conversion. I can use that anytime I'm dealing with a hydrogen. Oxygen over here on the right, that says underneath it 16. Again, that's 16 grams per mole. This just happens to be the case for oxygen and for hydrogen, that they're 1 and 16 very, very cleanly. There are some other values we're going to see later today where it might be like 35.5 for chlorine or 69 3/4 for gallium. There are some other values that we might use, but these ones came out very nicely. And expect that's often going to be the case. A lot of problems are set up in order to give you nice, clean values to work with. Let's go back to the problem though, because now we can actually do some math. I have 7.35, and that's my O2 in moles. All right. Now, of course, what I want to do is I want to convert that. So I'm converting that by multiplying it across by something that will cancel out moles of O2 and hopefully let me get closer to something in water, H2O. Well, actually, I have that. That was that 1 O2 gives me 2 H2Os. So I can multiply this 1 mole of O2 in the denominator by 2 moles of H2O in the numerator. And again, remember, this is not doing anything fancy or illegal. This is literally multiplying by a 1, essentially. 2 moles of H2O is 1 mole of O2. That's that equality we've been given. Now I've got moles of H2O. I'm not at grams yet, so I have to multiply this by something else that cancels out. For every 1 mole of H2O, I have to have some amount of grams of H2O. Now, I did do that quick circling in the periodic table. 16 is every oxygen. I have 1 oxygen in H2O. And hydrogens are 1, and I've got 2 of them. So 16 plus 1 is, better be 18 in my numerator, 18 grams of H2O. Okay, let's double check before we actually do the math. Moles of O2 cancels moles. Moles of H2O cancels with moles. And I'm left with grams of H2O. Perfect. Calculating that out across had better be 264. And in this case, now we've got it in grams, 264.6. And this is what we wanted to get, grams of H2O. Done. Now, at this point, we've done a lot of good work setting up this problem and carefully working down through it. But like I said, this is a relatively complex problem where we've got a lot of work to do converting between the periodic table and coming back. But it was really only about 2 steps. And it was very systematic in how we set it up and made sure that we could convert back and forth between those values. At this point, you might be thinking, but Eli, I want to go a little bit deeper into this. I want to know, when can I do the complex stuff? Sort of like what we've just been doing here. That was pretty complex. But I want to make it more common, because doing that sort of thing in chemistry, especially as you progress to higher levels, is actually relatively required. So what we're getting at here with complex unit conversions is that what we've done so far has really been converting one part of a unit. But problems may ask you to convert more. For example, going from miles per hour that I mentioned earlier to something like meters per second. That would require us to convert the numerator, miles, into meters, but also the denominator, hours, into seconds. No matter what, this sounds like it's going to be at least 2 conversion factors being used. So let's warm up with a problem very similar to the one that we actually just did. Let's take a look at this one. And of course, since we're going to set this up, instead of using my shorthand, which you notice got a tiny bit sloppy there at the end, let's deal with that nice, clean, clear setup with desired unit and given unit that we were playing with in some of the earlier problems today. Well, let's set in our desired information. That's got to be solving here like it asked for in concentration in SI units, and SI units would be moles per meter cubed. Now, given information, we had that tiny value, 0.036 grams of sodium chloride per milliliter. Now I have to cancel these terms out, and I can start wherever I want to, but let's start with grams, since we know that we're converting over to moles, and often canceling out the numerator value first is a little bit simpler for most people. So let's cancel out grams, since they aren't in the desired final unit, by the value they've given us here in the conversion factor A, 1 mole per 60 grams. Perfect. I didn't have to go to the periodic table. I didn't have to pull it up and calculate that myself. This was super nice. But let's go a little further. Now, I have moles now in the numerator, which is what I want. And milliliters still in the bottom. No good. I have to convert those milliliters to liters at least. That'll be a nice quick conversion because that's a power of 10. Milli means 1,000th. So converting it times 1,000 gives me that 1 liter. But I don't actually want it in liters. If I was solving for the second part of this question, molarity, I would actually be done. Now I have moles per liter. But the first part of the question was asking for SI, so we'll go one more step. To convert liters into meters cubed, we multiply by 1,000 again, because there are 1,000 liters, like I mentioned earlier, per meter cubed. If I have a cubic meter of water, for example, that's actually 1,000 liters of water. Now I'm done as far as my units are concerned. Everything cancels. The only thing I have left to do is do the multiplication across. And conveniently, since I'm multiplying by 1,000 and by 1,000 again, I'm going to go from that tiny decimal up to actually a relatively substantial value, 600 moles per meter cubed. Again, if I wanted to solve for molarity, which is often what we would do in a variety of actual laboratory problems, I would just not do this final step, and instead of having 600, if I'm dealing with molarity, I would just have 0.6. And in this case, since I would be ending with liters, 0.6 moles per liter. For the record, if we're doing a problem like this and we get multiple steps along the way, we always want to go back and double check the problem, because we could have a problem like this that was asking us for, instead of molarity, the most common thing we'd be likely to see, an SI unit instead. So just double checking that you're solving for the value we're looking for, because otherwise we can get too caught up in unit conversions and forget. Now what we just did there is actually really dimensional analysis. There are specific steps for doing step by step, the common sense sort of thing we've been doing in the past couple problems. Because we're carefully eliminating and canceling out those terms, we've really been doing these 5 steps of dimensional analysis. Now certainly, we don't want to get ahead of ourselves at any point. So the last thing, the last bullet point to remember is, like we talked about before, make sure you've done the right conversions before doing the math, especially if we're dealing with fractions or decimals or very big numbers like the last problem. Actually, for example, let's take a look at a real doozy of a problem. This one. There are a lot of moving parts to this problem. So I'll have to be careful here. Now, first of all, I'm going to need some values for chlorine and sodium. Even though those are here on screen, remember, if we had a problem like this in an actual class, we would probably be flipping to a periodic table here real fast because we might not be given it on screen. In that case, let's jump to periodic table. We would find chlorine over here, which has a value underneath it of 35.5. There we go, 35.5. And I need some sodium, which has a value of 23. Now again, these were given in the problem in this particular case, but if we hadn't had them in the problem, that's where we'd be looking. Underneath where it has the symbol, where it says sodium, right underneath that will always be a value, a number, and that represents its grams per mole amount. So let's plug these values in and take a look at them. First up, we'll start the way we always do with our desired units and our given units. And our desired in this case is to end in grams per liter. Not too bad. That sounds like a very common laboratory unit. And they've given us something a little bit crazy, these practical salinity scale units, the PSS. I'm going to need a little bit of space here. So I'm going to put these down here at the bottom. We start with 34 of those PSS, which is really 34 grams per 1 kilogram. Again, just pulling that unit here out of the original problem, not these conversion factors necessarily, but those are ones we're going to have to use. Now again, like we talked about before, we could start anywhere. But let's start by converting the sea salt into something we know more about, which is actual salt ions or chloride ions. So I'll convert that into chloride ions with conversion factor D as in delta. Now I've got the salt canceling out, but I need to cancel out my ions. So, I don't have anything really in the set of conversion factors that cancel out the ion, but I do have something that converts the ion into moles instead. That's conversion factor C as in cobra. Now notice we rounded here a little bit. Like I said, chlorine is 35.5, but considering the amount of math I'm doing in this problem, often a small amount of rounding, like rounding 35.5 down to 35, or even 1.8 grams here down to 2 perhaps, would have been something more convenient for plugging in the math, especially if we have to do it longhand. Now at this point I have moles of chlorine, but I want something in full salt, right? I want sodium chloride. Well, conversion factor B as in Bravo reminds me that, hey, in that sodium chloride molecule, I have exactly 1 chloride ion. Sodium, 1, chlorine, 1, sodium chloride. So I have a 1-to-1 relationship. Perfect. Now I have moles of sodium chloride. I'm getting close. I'm going to need conversion factor, though, that gives me sodium chloride, converting it into something in grams. That's conversion factor E as in echo. All right, great. I have grams. That's what I wanted. I'm almost done. Now I've just been playing with that numerator. I do have grams of sodium chloride. I have finished my numerator conversion, but now I've got to do something about that denominator. I can't end in kilograms. All right, now I have conversion factor A as an alpha, which has 1 kilogram per 1,000 milliliters. And you might say to yourself, well, Eli, we're pretty much done because 1,000 milliliters is a liter. But remember, we just converted to milliliters. We haven't actually converted explicitly to liters. We have to still multiply that by 1,000 milliliters per liter, because even though 1,000 milliliters is a liter, we have to literally convert the value in order to cancel out the terms that don't apply. Otherwise, we haven't actually done the full math on the problem. Now, if I multiply this all out across, I hope that I get out the value here on screen of about 31.3. And again, depending on where we rounded, if we had rounded the 1.8 to 2, if we had rounded the 58 grams to 60 grams, your value might be off a tiny bit, somewhere between 31 and 32. But as far as a multiple choice test would be concerned, that should get you to the answer. And certainly, if I'm trying to get a very specific value, I would have kept all of them in there and used the calculator. Again, doing any of that fancy math, though, plug into the calculator, make sure we've got all of our eliminations done, and really, we are done. Done with that learning objective. We have one last one. This is where we're ending, which is to actually do a full unit conversion problem when, sort of like I've been building you up to, the conversion factors are not completely given. Now, certainly, there are a lot that you can memorize first. For example, that there are 12 inches per foot, or that there are 3 feet per yard. But often a lot of chemistry conversion is going to just be different powers of 10, like centimeters to meters or meters to kilometers. And as far as conversions go, remember, they can go both ways. We can convert up to a higher number. We can convert down to a lower number. AKA, we can flip them. For example, I could say that $1 is 100 cents. I could say that 100 cents is $1. In either case, I'm still multiplying by 100 cents per $1 or $1 per 100 cents, which is a one-to-one relationship. I'm essentially multiplying anytime I do a unit conversion by multiplying by 1. Now, in many problems, like I said, you won't get the lovely fractions or the lovely equalities that we've been using so far. We might get something that hints at the equality or sets up our fraction for us, but we have to pay a little bit more attention. Further, there are some problems, like I said, that don't really rely on specific units or amounts to be used. For example, the powers of 10. Classic case that we see all the time in chemistry, where we go from milli to kilo of anything. You know exactly how many powers of 10 that has to be. I could go from milligrams to kilograms. I could go from millibytes to kilobytes. Doesn't matter what that second half thing is, milli to kilo is always the same conversion factor of 10. And there are some simple problems that we might use every day, like cups and gallons or feet and inches. But as far as metric power conversions that chemists have to memorize, that's something you might want to toss on flashcards. The more problems you start doing, then the more you start noticing values that are frequently converted in between. Right now, it might seem like a little bit of extra work, but it will come in handy consistently as we're working. Specifically, if there's something that I would have you memorize first, I'd have you take a look at these. There's a nice little mnemonic here I'll toss down here underneath to go from the high values, kilo, down to the tiny values, pico. And that's kangaroos hopping down driveways, chasing monkeys, making nematode pies. I don't know if a nematode pie is delicious or not. Maybe you want that to be a Nutella pie. That's actually how I changed this mnemonic for myself. Nutella pie, delicious. However, let's take a look at some sample conversions, something that we might want to do playing with this huge list of powers of 10. Take this one, 53 kilometers, and we want to convert it into some amount of centimeters. Certainly, off the top of my head, that sounds like I'm going to get an enormous number of centimeters, but let's just double check exactly how much bigger. We start with 10 to the third, that's kilo, and we're going down here to centi, which is 10 to the negative 2. So I've gone from a 10 to the 3, and I'm getting smaller and smaller and smaller and smaller and smaller by powers of 10. I've moved 5 powers of 10 over, from a big value to a very small value. It's like going from 1 football field, which is big, to 320 feet, which is significantly smaller. So we know those 10 powers of 5, that means we're essentially multiplying by 10 to the 5th to get this new value. Multiplying by 10 to the 5th is moving 5 decimal points over to make it a bigger number. So notice 5 zeros added onto that 53. Let's try another one. How about this meters to micrometers? That little lowercase looking squiggly u thing, that is a mu for micro. So it starts with meters, which is 10 to the 0 or just 1. And it's going all the way out here to 10 to the negative 6. Again, moving to a much smaller unit value. And this time it's, well, from 0 to 10 to the negative 6. So it's 10 to the negative 6, or 6 powers of 10 that we've moved down. And since it's still to a smaller value, that means I'm going 6 decimal places, because it's 6 powers of 10, to the right. Of course, because I had 0.27, I have 2 decimal points to get that to be a 27, and then I'm tacking on my additional zeros. So 2 places plus 4 zeros is my 6 total places I've moved over to the right. Both of these times that we moved over to the right, what if maybe we went the other way? let's take a look at this. Going, in this case, from nanometers to centimeters. So we'll start over here on the right at nano, 10 to the negative 9. And we're moving to centimeters, like we did on that other problem. But we're moving from nano to centi. So we moved from 10 to the negative 9 to 10 to the negative 2. So I'm going to a bigger unit. So the total amount is going to be smaller inherently. And I've gone 7 powers of 10. I've gone 7 powers of 10 bigger as far as my unit is concerned. So the actual value must be 7 powers of 10 smaller. So I'm going to move the decimal point 7 to the left to make the actual value smaller. Let's do one more. In this one, I'm going from picometer to micrometer. Here's pico, way down there at 10 to the negative 12, to micro, 10 to the negative 6. And we went to a bigger unit, and the unit is bigger by 10 to the 6. So we need to make the actual value, because I've changed units, to be bigger. The value must be smaller by that much, by 10 to the 6. So moving the decimal point 6 to the left to make it smaller gives me that 2 places to get the 19 underneath the decimal, plus the additional 4 zeros for the other 4 decimal places I have to move over. Done. Well, I kind of want to do a couple more. Let's run through this one like we've done so far, step by step. First, set up our desired unit and our given unit. So looking at the problem, we want to know what is this in SI units, and it's some amount of stuff per some volume. Well, my SI unit of stuff is moles, and my SI unit of volume is meters cubed. So that's what I want to end with, but they've given it to me in millimoles per liter. Okay, well first up, I want to get rid of that milli term. And any milli is 1,000th. So it must be milli of a mole, so 1 mole per 1,000 millimoles. Good so far. But now I want to convert, and now I've got moles in the numerator. Let's get rid of that denominator stuff. So liters. I can convert liters into something that might be a little bit easier to deal with the math on. Let's deal liters to milliliters. I know what you're thinking. The math doesn't look immediately easy, but this is a much more convenient unit for most people to convert to milliliters, because milliliters to centimeters cubed is a 1-to-1 relationship. Instead of having to memorize a bunch of different conversions, like there are 1,000 liters per meter cubed, or how many centimeters cubed there are per meter cubed, instead of doing a lot of extra conversions in my head or memorizing a bunch more on flashcards, most people memorize this. 1 milliliter per 1 centimeter cubed, because it's a perfect 1-to-1 relationship, and you never have to think of it again, besides that one flashcard. So now I've converted to milliliters. I have centimeters again, but I want to know how many centimeters are there in a meter cubed. Watch out. It might help to do a little picture here. Picture, let's say I want to have a meter cubed, but I have centimeters. So remember, there are 100 centimeters per meter, because I want to keep centimeters, because that's the term I'm canceling out. So that means 100 times 100 times 100 will equal 1 meter cubed. Whew. Okay, I didn't want to have to remember that conversion in my head, that there are 10 to the 6 centimeter cubes per meter cubed. Sometimes just drawing a quick picture and actually seeing it visually in front of you helps you just do the math a little bit simpler. Keep all of the numbers in terms of the powers of 10 or the number of zeros all in one place. And really conveniently, this turns out perfectly to cancel out all of those zeros, so we're left with exactly the same value, 4. Apparently 4 millimoles per liter is 4 moles per meter cubed. Actually, that means anytime we have millimoles per liter, that will equal directly moles per meter cubed. Now, I know you might be thinking, well, maybe I should put that on a flashcard, but the likelihood of seeing that exact one again is pretty small. And in fact, not only that, we know how to do it again with each of those different steps along the way. Let's do another one here. Again, keeping track of the desired unit, the given unit, and doing step-by-step analysis But additionally, we're given some weird stuff in this problem. We're given a unit, a barn equals this amount of meter squared, and then we have additional power conversion asked about in the question. We have to actually deal with millibarns. So watch out. In some of the higher difficulty problems, you might get a nice conversion, barns per meter squared like this, in the problem, and then the actual question forces us to solve for something else, like a millibarn. We don't want to mess up in setting up this conversion then. We'll go step by step. Desired is in millibarns. Given, well, we have this estimated value of 2.4 times 10 to the negative 29, so that must be our given value that we're going to convert over. Okay, meters squared, I can't go right to millibarns. Let's convert to barns. That was the first thing I underlined here in the problem. Perfect. Again, making sure my meters squared is in the denominator, so I'm canceling it out. Barns is in the numerator. Great. Now, milli is 1,000th, but I want to end with milli. So I have 1,000 millis per one barn. Millis had better be in the numerator, and there's 1,000 of them, so multiply by 1,000. Done. Multiplying straight across does absolutely cancel out a whole bunch of those powers of 10, and we get 2.4 times 10 to the second, or 240. Great work so far. This is a sort of problem that takes a little bit of extra work, a little bit more conversion, but it's something that turned out quite nicely once we set it up carefully and canceled out those terms. Now notice for that one, while millibarn happened to be an actual power of 10 value for distance, very similar to our number line earlier, it's definitely beyond the scope of what most chemists would have had memorized. Some conversion factors would be just true for that one problem, not something that we would necessarily put on a flashcard or try and remember for the future. And anytime we happen to be converting weird values or specific constants are involved, anything that's non-standard, we should be given the conversion factors in some form so that we can set up the problem correctly. Otherwise, we wouldn't be able to do our dimensional analysis. So let's look at one final problem for the day then. And no matter what, when we're tackling a problem like this, and we're trying to figure out which one to solve first, we're going to need to make sure we have everything in place to actually get to the end value. So we've got a question about how many millimoles of H2. That must be what we're actually trying to figure out. And the 10 grams of water, that's what we've been given. So I'm going to need something that converts grams of water to millimoles of H2. I don't have a whole lot to work with. For water, I do have one relationship that's going to convert moles of something to moles of something. In this case, I have 2 moles of H2, and I have 1 H2O. That's nice, but it doesn't deal with grams. All right, that makes me think I'm going to have to consult our handy periodic table. So jumping to the periodic table, for either of those two problems, we had to deal with hydrogen, which you may remember is 1, and oxygen, which you may remember was 16. Of course, this is grams per mole. 1 gram per mole for hydrogen, 1 times 16, 16 grams per mole for oxygen. All right, well, let's jump in and actually put this into play with our careful analysis like we've been doing from the very beginning. Let's start with the first half of this problem with water. So we desired to have those millimoles of H2, and we were given 10 grams of H2O. All right, let's take, well, I have to convert to moles as soon as possible, ideally, so that I can actually use that equation here at the top. So I'd love to convert moles and grams right away. And I have 16 grams per mole for oxygen, 1 gram per mole for hydrogen, and there's 2 of those in water, so 1 plus 1 plus 16 is that 18 grams that we played with earlier. But again, since I'm canceling grams, it must be in the denominator. Okay, now I'm in moles, and from the formula here at the top, I know that there are 2 to every 1 water. Again, 2 in the numerator because I'm canceling out the water moles in the denominator. Now I have to convert over moles to millimoles because that's the problem end. I have to get those millimoles. And there's 1,000 millimoles by definition per every mole, because that's a nice power of 10 conversion. Carefully setting it up, it looks like we've canceled everything out. And even on your scratch work, you might just go through carefully so you don't lose the unit completely and just cancel out to double check. Gram in the numerator cancels gram in the denominator, mole cancels mole, and finally mole cancels mole of the correct type. We're left with millimole correctly. Perfect, we did our math right, and now we just calculate values across. 10 divided by 18 times 2 times 1,000 had better be about this 1,111 value. Cool. Let's keep going. Let's do our second part of this question. We're actually accounting for something a little bit different. Make sure we don't miss that now we're playing with hydrogen peroxide, and we also have a different formula for hydrogen peroxide. Let's set it up. Desired, well, we want to end with millimoles of H2 still, but we're given, in this case, 10 grams of hydrogen peroxide. My first step would really be the same. I want to get this into moles as soon as possible, but let's just make sure we don't miss something. In this case, we have oxygen times 2. So 2 oxygens, which were 16 each, is 32, plus a 2 hydrogen, which is another 2, gives me 34. Now I have a 1-to-1 conversion from hydrogen to hydrogen peroxide. And then, of course, I do have to make sure it's millimoles, and a millimole is always 1,000 millimoles per mole. Again, double checking before I actually do the math on this one would be a smart bet. Canceling out the grams from the beginning. Moles of hydrogen peroxide cancel. Moles of just hydrogen cancel. And I am left with millimoles successfully. Perfect. 292 millimoles. Done. That is what our calculation gives us, and we're finished with both of these problems. These are the last 2 problems of our session. So good work today. Keep up your practice with chemical computations. Keep up your practice with conversions. And I'll remind you, this takes effort at first. But once you're proficient and you can really work through these problems at speed, you'll make short work of these the next time you see them, and as you consistently put in more of that effort. Good luck studying.